This video is a continuation of effective nuclear charge. We're going to use effective nuclear charge to start discussing trends that we find on the periodic table. So effective nuclear charge, let's call it E in R, is equal to Z, the actual charge, minus the shielding constant sigma, and we approximated the shielding constant sigma to be similar to the number of inner shell electrons or core electrons in an atom. So just for an example, let's look at sodium. Sodium has 11 protons in the nucleus. That's its effective, that is its nuclear charge. And sodium has 3 shells around the nucleus, 2, 8, and 1 electron are in each of those shells. So that's a total of 11 electrons to go with 11 protons. The electrons in the first shell and the second shell are called inner shell electrons or core electrons, and the electron that is in the outer shell is called a valence electron. So the effective nuclear charge that the outer shell electron feels from the nucleus is 11, the actual nuclear charge, minus the 10 core electrons equals 1 positive. All right. So what we're going to look at today is looking at effective nuclear charge. We'll use that as a predictor of atomic size, ionization energy, and electron affinity. So in the same period as sodium is the element chlorine. Chlorine has 17 protons, 2 electrons in the first shell, 8 electrons in the second shell, and 7 electrons in the third shell. And again, remember that whatever group the element is in, that helps us determine the number of valence electrons for groups 1, 2, and 13 through 18. So chlorine being in group 17 has 7 valence electrons, or we use the old naming system, group 7A. Those elements in group 7A have 7 valence electrons. So Z effective is equal to 17 minus, again, the 10 core electrons equals 7 positive. So the effective nuclear charge that the outer 7 electron sees from the nucleus of chlorine is 7 positive, whereas the effective nuclear charge that the outer 1 electron in sodium sees as the effective of 1 positive. So what's the implication of that? Well, sodium is a fairly large atom, and we'll say it's about 186 picometers. Oops, lost my picture. 186 picometers. Maybe more than that, depending on which table you're using to determine atomic radius. So that's the radius, 186 picometers. That's half the distance. That's from here to the center. All right, and then we look at chlorine. Chlorine's in the same period, and it has more protons, and it has more electrons, but its atomic radius is only 99 picometers. So I think it throws students a lot of times that, yeah, we're adding more protons, we're adding more electrons, looks like the atom should be larger. But what we're not taking into account is, first of all, a proton is very, very small. It is located in the nucleus, and the nucleus makes up a very, very, very small amount of the volume of an atom. The volume of the atom is made up by the electron cloud around the nucleus, and so even though this has more electrons, it still only has 3 shells, the same as sodium. And because there's more protons in the nucleus, that pulls the electrons in closer to the nucleus. Opposites attract, so the positive nucleus attracted to the negative electrons pull those together. So we see a decrease in the size of the atom. Now, when we look at the next element on the periodic table below sodium, that would be potassium. And potassium has 19 protons. It has 2 electrons in the first shell, 8 electrons in the second shell, 8 electrons in the third shell, and 1 electron in the fourth shell. Potassium is the first element in the fourth period. So Z effective is approximated as 19 minus the core or inner shell electrons, which is 18. So we get a Z effective of 1 positive again. But what we need to remember is the distance from the nucleus to the outer shell has increased because we've added another shell to the atom. And so even though numerically we have 1 positive, it will be less than 1 positive due to that distance. So even knowing that, and knowing we've added an extra shell, watch what happens to the size of the atom. Potassium's size is larger than sodium, and it's 227 picometers. All right, we could look at chlorine. Or not chlorine, let's look at bromine. So bromine has 35 protons, 2 electrons in the first shell, 8 in the second, and the third's a little tricky because we add 8, then we add 2 to the fourth, and then we go back and go through the transition metal, so there's 18 here in the third energy level because we've gone through we had the 3s electrons, the 3p electrons, then we did the 4s, then we did the 3d, and there's 10 of them, that's where we get 18, and now we're back into the 4p, and we add 5 more for a total of 7. So bromine is in the same group as chlorine, but it has an extra shell. So Z effective for this would be 35, that's the nuclear charge, minus the number of core electrons, which is 2 plus 8 plus 18, which is 25. Oops, I mean 28. 28. And that's a Z effective of 7 positive. Now, these both have a Z effective of approximately 7 positive, but again, the outer shell electrons in bromine are further away, and so we would expect it to be a little less than 7 positive. So because of that, because it's got an extra shell, the nuclear influence is not as great, we would expect bromine to be larger than chlorine, and it is. It's 114 picometers compared to 99 for chlorine. All right, so you say, why do I need to know this? Well, one of the things we have to do is we have to predict the size of an atom. That's going to be important in bonding coming up. So what is the trend for atomic size? So atomic radius is generally what we measure, half the distance, or the distance from the outer shell to the nucleus. So atomic radius is what we're going to be measuring. And let me just say something about atomic radius. When you Google this, or when you look in a book, you may get different values than what I'm going to talk about, like we saw on the last slide. And that depends on what you're referencing. And maybe newer tables have different ways of measuring atomic radius. And so they may have a more up-to-date value than my textbook. So you may see some changes, but what we want to really know about atomic radius is the trend. We want to know what happens as we go across the periodic table from group 1 to group 18. And we want to know what happens when we go down the periodic table from period 1 to period 7. So those are the trends we need to know. And again, we need to know these trends in order to predict chemical bonding scenarios that will be coming up. So as we go from group 1 to group 18 across the periodic table left to right, the atomic radius decreases. And the reason why it decreases is as we march across, we're adding more protons into the nucleus. The core electrons are remaining the same. Yes, the outer shell electrons are increasing, but the effective nuclear charge, the charge the outer shell electrons see from the nucleus, increases. That draws the electrons in closer to the nucleus, and so therefore the atom gets smaller as we go left to right. It decreases. Now, as we go from top to bottom, the atom gets larger because we're adding more shells. And even though the Z effective is all 1 positive for everything in the first group, because we are adding shells and we're getting further and further from the nucleus, those outer shell electrons are, that reduces the attraction of the outer shell electrons to the nucleus and the atom expands. So again, if you want to remember this trend as we're adding more shells to the nucleus, that is fine, but what you want to remember is it increases as we go from top to bottom. Now, are there places where we would see this trend not agreeing? Absolutely. Those are called anomalies, and we would have to get into a further discussion as to why those anomalies occur, but that's beyond the scope of this presentation. We just need to know the trend as we see it here, so then we can start talking about other periodic trends such as ionization energy and electron affinity. So let's talk about ionization energy. First of all, you have to know the definition of ionization energy, and it's very specific. Ionization energy is the amount of energy required to remove an electron from a gaseous atom, or an atom in the gas phase. And the reason why it needs to be in the gas phase is when we look at something like sodium, which naturally occurs as a solid, when you try to pull an electron from sodium in a solid matrix, energy is going to be drawn from the adjacent sodium atoms. And so that's going to affect the overall energy required to remove an electron. Think about sticking your finger in syrup, and as you pull your finger out of the syrup, you can tell the syrup is clinging and the other surface molecules of the syrup are sticking as well. So we have to have an element in the gas phase, an individual atom. We are going to apply energy. It always requires energy to remove the electron. And what we will end up with is a sodium cation. Remember, cations are positively charged ions in the gas phase. So the general form of this equation would be any element in the gas phase plus energy, and sometimes people leave the energy off, ends up as X ion plus the release of an electron. And I didn't put that up here, and I should. The release of the electron. All right, so that's what we're looking for ionization energy. Individual atom in the gas phase, how much energy is required to remove the electron from that atom and forming a cation. So the trend is related to Z effective. So we know as we go across the periodic table, the Z effective increases, which makes the attraction of the outer shell electrons to the nucleus greater. It causes the atom to shrink in size. And so we would expect an increase in ionization energy because of this stronger attraction and smaller size. We'd expect an increase in ionization energy, called IE, some people call it IP for short, as we go across the periodic table. Now, as we go from top to bottom from period 1 to period 7, we would expect a decrease in the ionization energy. And the reason why is, again, Z effective remains fairly similar from everything in a particular group, but as we add another shell, as we go from period 1 to period 2 to period 3, there's less influence of the nucleus on that outer shell electron, making it easier to remove the electron from the atom. So that's why ionization energy decreases as we go from top to bottom. How much does it decrease? Well, let's look at a couple examples. Lithium is up here at the top. It's a metal. And so we're going to take lithium, we're going to add energy, and it's going to become a lithium positive ion in the gas phase. Again, it was in the gas phase over here as well. Plus the loss of an electron. That's ionization energy. So for lithium, the first ionization energy is 520 kilojoules per mole. All right. If we drop right below that and look at sodium, sodium in the gas phase loses its electron, becomes sodium positive, plus the loss of an electron. It's 899 kilojoules per mole. Oops, I made a mistake there. Let's just cut through that. I knew that sounded too high. It's 497. It's 496 kilojoules per mole. 496 kilojoules per mole. Because that wasn't making sense, right? This was a lot larger than this number, and we said it decreases as we go from top to bottom. All right, 496 kilojoules per mole. All right. So then let's compare that to fluorine and, well, let's at least compare it to fluorine. All right, so fluorine's in the same period as lithium. So with fluorine, we would be taking monoatomic fluorine, not diatomic, its natural form, but monoatomic fluorine, and we would remove the electron. It would become positively charged in the gas phase, loss of the electron. What do you think the ionization energy would be? With a Z effective of 7 positive versus lithium at 1 positive, what do you think the effective ionization energy is? (1,681 kilojoules per mole. Over 3 times more energy required to remove an electron from fluorine than lithium. That's important to remember. The ionization energy tremendously increases as we go across the periodic table. Why? Because the Z effective has increased. The atomic size has decreased. The effective nuclear charge has increased. Those two things combine to make it harder to remove an electron from the non-metal fluorine than the metal lithium. So, this is part of the puzzle that we need to know. And why does sodium chloride form a sodium ion and a chloride ion and form an ionic bond between them that holds that compound together? Why isn't it that sodium forms a negative ion, or why isn't it not sodium negative ion and fluorine positive ion? Well, here's the half of the reason. That is, the ionization energies for metals are much less than the ionization energies for nonmetals. So lithium, being a metal, has a low ionization energy relative to fluorine, which is a nonmetal, which has a high ionization energy. 3 times the ionization energy in fluorine than lithium. All right, let's look at chlorine. So chlorine's in the same period as sodium, and we know sodium chloride is Na positive. Let's write that over here. We know that it's an ionic compound that consists of these 2 ions bonded together. So we have chlorine in the gas phase, and it loses its outer shell electron, one of its outer shell electrons, I should say. becomes a positive ion plus the loss of an electron. All right, its ionization energy is about 1256. 1256. All right, 1256 kilojoules per mole. Less than fluorine. Why? Well, chlorine's got an extra shell around it. Those electrons are further from the nucleus. So, this is what we need to know. This is the reason why ionic compounds, generally the metal is a positive ion and the nonmetal is a negative ion, because the nonmetals have high first ionization energies and metals tend to have low first ionization energies. All right, we're going to stop here. There's going to be another video. That video is going to discuss the anomalies that occur in ionization energies, and then we will introduce electron affinity.